Okej, bukur shumë. Është mirë se vini në seminarin e Departamentit të Matematikës. Kam kënaqësi dhe është nder për ne që të fillojmë një seri të seminareve të tilla me një folse e cila ka qenë studente në Universitetin e Prishtinës, e tash është postdoktorante në Universitetin e Parisit Saclay, është në Orsay, doktor Vlerë Mehmeti. Siç jeni të njoftuar, seminari i prezantimit do të mbahet në gjuhën angleze. Qëllimi është që të ketë një prezantim për një audiencë sa më të gjerë. Prandaj edhe Vlera do të filloj me materie që është relativisht e përgjithshme, është mjaft e përgjithshme, ashtu që të ketë mundësi përqasje edhe dikush që është student, edhe dikush që është studiues. Pa zgjatur më tej, po ja jap fjalën Vlerës, e cila pastaj, nëse ka mundësi, brenda 45 minutave parafusisht, na bën prezantimin dhe ndërkohë nëse ka dikush pyetje, ju lutem i shënoni në chat dhe ju japim fjalën, por pastaj në fund do t'i kemi disa minuta për diskutim nëse keni pyetje. Faleminderit shumë. Tash, now we switch to English. Blair, the floor is yours. Thank you.
Faleminderit shumë Qëndrem. So, hi again, everyone. Many thanks again to Qëndrem for the invitation. It's really a pleasure for me to speak at the seminar of the University of Prishtina, which is where I got my bachelor's degree. So today I will be speaking of the existence of solutions to systems of polynomial equations. An example will always be given by the concrete case of polynomial equations induced by quadratic forms. So in order to study this question, we are going to use a geometry called non-Archimedean, which is very useful for the comprehension of arithmetic phenomena, and which, is characterized by peculiar properties which are very different from those of our real world, in the sense of those of Euclidean geometry. So what are some instances of this weird behavior? So, for example, in this non-Archimedean geometry, every triangle is going to be isosceles. This means that no matter what triangle we take, at least two of the three edges are going to have same length. Another strange behavior is that every disk has several centers. We don't have disks with a single center anymore. And it's even worse than that. Actually, it's that every point of the disk is a center. So this means that any point we take inside of the disk, well, its distance from the sort of border of the disk, the accompanying circle, is going to be a constant that I denoted here by R for radius. So another very strange thing that happens here is that in a certain sense, integers, meaning numbers in Z, are always smaller or equal to 1. So that in particular, the distance between any two integers is also always smaller or equal to 1. Now, as we can notice here, in all of these three examples, these peculiar behaviors are induced by some sort of notion of distance, here between the vertices of the triangle, here between the points in the disk and those in the border of the disk, and here, well, it's simply the distance between integers. And this is how one induces a non-Archimedean geometry. So let's start by we will now construct a concrete example of such a geometry by using norms on Q, on the field of rational numbers. That's where we are going to construct our geometry. So let me start by recalling a bit some basic things about norms on Q. One example is a really typical one. It's the usual absolute value, which is defined as follows. So for a rational number x in Q, we define its absolute value to be simply itself when x is non-negative, and minus itself when it is. So we know that one way, for instance, to construct the field of real numbers is to simply take Q and complete it with respect to this absolute value. So here, this means that we take Q and we add to it all of the limit points of Cauchy sequences over Q with respect to this absolute value. And now we obtain the field R, where all of the Cauchy sequences have a limit. And well, the notion of absolute value, this absolute value does induce a distance in the field of real numbers. We can simply say that the distance between any 2 points is, well, the absolute value of their difference. And this is the same way that any norm can induce a distance on the field of real numbers. Now, one may ask oneself whether the geometry that we obtain this way is non-Archimedean. Well, we already all know that that is clearly not the case, because the Euclidean geometry does not satisfy those weird properties that we just saw. So in fact, the absolute value is what we call Archimedean, in the sense that it satisfies the so-called Archimedean property, which states that, well, if we take a rational number x, then we can find a natural number n such that, well, by taking n copies of x, then we are going to have a number whose absolute value is going to be larger than 1. So this is going to be a number which in terms of the absolute value in this geometry with this distance is going to become relatively big. And this is what fails to happen when we consider non-Archimedean geometry. So we have this classical norm on Q. What other kinds of norms can we obtain? Well, it turns out all of the other norms on Q are going to give us a non-Archimedean geometry. So let's construct an example. The example of the p-adic norm. Let's take P to be a prime number. So this means that P is strictly larger than 1 and that it is divisible only by 1 in itself. It has no other divisors. Now, how can we define this p-adic norm? Let's do it. Let's start by doing it for integers. If we take an integer n, a non-zero integer, let's denote by m the largest power of p that divides n. So this means that p to the power of m divides n, but p to the power of m plus 1 does not divide n. We can, of course, always construct such an m for a non-zero integer n and for a fixed prime number p. Here is an example. If we were to take p equal to 3 and n equal to 18, well, then one has m equal 2, because 3 to the power of 2 is the largest power of 3 dividing 18. Clearly, 27 does not divide the number 18. So then what we do is that we define the p-adic norm of this integer n to be simply 1 over p to the power of m, with m given as right here. So for now, we've defined this only over z, only over the integers, the non-zero integers, but we can generalize it from here to the entire field of rational numbers as follows. So let's write x as the division of some fraction. So fraction of a over b with a and b integers. And then we are going to define the p-adic norm of this rational number as being, well, 0 if x is 0. If it's not 0, then neither a or b are 0. So we are simply going to define it as the division of the p-adic norm of a with the p-adic norm of b. And one can show quite easily, in fact, that this does not depend, this definition, it does not depend on this representation of x as the fraction of a over b, because as we know, this is not necessarily unique. And I haven't added any additional hypotheses to make it unique. So this is now a new norm over Q. It's what we call a p-adic norm. And here it's very different from the usual absolute value that we just saw. And here are some examples of calculations with this p-adic norm. So for starters, here the sequence p to the power of k is not only convergent with respect to the p-adic norm, but it converges to 0 when k tends to infinity. This means that the larger k becomes, the smaller in terms of this norm, p to the power of k is going to become, which is very different from the case of real numbers, where the sequence p to the power of k with respect to the absolute value tends to infinity. So it's not even convergent. Here are some concrete calculations. So the three-adic norm of 18, thanks to the calculations that we already figured out right here, is 1 over 9, because, well, we said that 2 was the largest power of 3 to the power of 2 is the largest power of 3 to divide 18. So this is simply 1 over 3 squared, which is 1 over 9. Similarly, seeing as 2047 is odd, 2 to the power of 0 is the largest power of 2 dividing 2047. So its two-adic norm is simply 1. And in the same spirit, the norm of the two-adic norm of 2048 is going to be 1 over 2 to the power of 11, which is this very small number, very small in terms compared to 1 that I've written down here. And if you compare these two numbers, you can realize that, in fact, with this notion of distance induced by the p-adic norm, the number 2047 is considerably larger in a certain way than the number 2048, which is also very different from when we use the absolute value. And this is just a special case of a more general phenomenon, which is that the more the prime number p divides an integer n, the smaller somehow this n is going to be. Okay, so these sort of norms that induce non-Archimedean geometries, they satisfy an inequality called the ultrametric inequality, which is at the core of all of the differences between the Euclidean geometry and these new non-Archimedean geometries. This is the so-called ultrametric inequality, and so it accounts for all of these strange behaviors that we just saw in the beginning. So the ultrametric inequality states that for any two rational numbers x and y, the p-adic norm of x plus y is smaller or equal to the maximum of the p-adic norms of x and y. And in particular, for example, we can show quite easily that if the ultrametric inequality is true, which it is for p-adic norms, then if the p-adic norm of x is strictly smaller than the p-adic norm of y, well then the p-adic norm of the sum of x and y is equal to the larger of the two, so the p-adic norm of y. And this is very useful when, well, computing things, let's say. Here is an example. We're going to see an example of such a computation soon, but first of all, let me just make a remark. So this ultrametric inequality, it's much stronger than the usual triangle inequality we encounter for general norms, which says that the sum of the norm of a sum of two elements is smaller or equal than the sum of their norms. For example, this is the inequality satisfied by the absolute value and also by the p-adic norm, except that the p-adic norm also satisfies this stronger inequality. And the absolute value, of course, does not. So how does this, for example, help us obtain those weird properties that we saw in the beginning of this new geometry? So in the beginning, I told you that here, every triangle is isosceles. So let's take a triangle with vertices x, y, and z. Basically, we took three numbers x, y, and z, and we're looking at the triangle induced by them. Now, if it so happens that the lengths of the edges of this triangle, which are given by simply the p-adic norms of the differences of these numbers, are all the same, then that would mean that the triangle is equilateral, meaning that all of the lengths of the edges are the same. So in particular, of course, it's going to be isosceles. Now, what if this is not the case? Let's suppose that at least one of the lengths of the edges here is different from the others. So without loss of generality, let's assume, for instance, that it's this edge, its length, that is shorter than this one. So the p-adic norm of x minus y is strictly smaller to the p-adic norm of x minus z. Then what the ultrametric inequality tells us is that, well, the p-adic norm of y minus z is smaller or equal to the maximum of the lengths of the other two edges of the triangle. So by using finally this part, thanks to this assumption, one can deduce that the p-adic norm of y minus z is the same as the p-adic norm of x minus z. So basically that these two edges have same length, and hence that the triangle is isosceles. Okay, so in the beginning, I mentioned that one way to construct the field of real numbers was to take Q, the field of rational numbers, and complete it with respect to the absolute value. Now, one can do the same thing with respect to the p-adic norm. We take Q, we add to it all of the limit points of its Cauchy sequences with respect to this norm, and then what we obtain is a new field, which is called the p-adic field. Its elements, we are going to call them p-adic numbers. Now, this field was introduced about around the end of the 19th century. And in the beginning, mathematicians were a bit skeptic about, well, how useful it was going to be in mathematics. They thought that it might be a bit too abstract to be useful. Well, things started developing, mathematics started developing in such a way that mathematicians became increasingly conscious about the usefulness of these objects, of these p-adic fields. And now they play a very important role in many domains in mathematics. You can't really bypass them. So a natural question here is, what do these p-adic numbers look like? We're encountering a new field. We're saying that we have these new numbers. So how can we describe them? Well, it turns out that there is a way to do this that somewhat, at least up to a certain point, mimics the decimal expansion of real numbers. So here, of course, the role of 10 is going to be played by the prime number p. So what does this mean? Well, if we take a p-adic number x, then to it, we can associate a p-adic expansion, which looks like this. So it's an infinite sum. It's a series of powers of p, starting from a negative power of p and going on infinitely, and where the coefficients reappear sort of play the role of figures, which are integers ranging from 0 to p minus 1. For example, this also makes us think of the writing of integers in base p. Of course, then we would start from a0 and the sum would be finite. So this is a sort of generalization of that principle. And now we remark here that this p-adic number x, we can see it as a limit of the following Cauchy sequence here of rational numbers. So all we have to do to construct this Cauchy sequence is to truncate the series at a random nth term. And this will give us this finite sum, which is now a rational number. And this series is going to be a Cauchy one with respect to the norm, to the p-adic norm, because we saw that p to the power of n tended to 0. And the limit point, well, it's going to be our p-adic number x. So let us now see, we have this p-adic analog of R, this field which we're calling QP, and the p-adic numbers. So let us now see what are some of the fundamental differences between these two types of fields, over the field QP and the field R. The first one is actually quite nice. It says that an infinite sum, so a series over QP, is going to be convergent if and only if its general term converges to 0. So this is very different from R. In R, this would not at all be sufficient. and it's much nicer in a certain sense. And that's why sometimes this property is called a student's dream. Another property, which is not so nice, is, well, when it comes to the exponential, another difference. So we know that the exponential function over R, we can define it by using this series. Now this series is going to be convergent everywhere on R, meaning that the exponential function can be defined like this everywhere on R. We define the exponential the same way over QP, meaning by using this infinite series, except that here, this is not going to be a series that is convergent everywhere. It has a finite radius of convergence, meaning it is bounded by some constant, which depends only on P. And so the exponential is not defined everywhere. And this is very different from the real case and is as at the root of many differences when trying to study, for example, differential equations over QP. It means that the approach has to be much more different. It has, well, yeah, to be very different with respect to the one over R. So one last property is that, well, we know that over R, the square roots of negative numbers don't exist. This is no longer necessarily true. This is not necessarily true anymore over the fields QP. For instance, if we were to take P congruent to 1 modulo 4, then the square root of -1 does exist in this p-adic analog of R that we're calling QP, meaning that, well, in a certain sense at least, the imaginary number I exists as an element of QP. Okay, so talking about the imaginary number I, one natural question is, okay, so we're constructing QP like we constructed R by completing Q. What about C? Can we construct some sort of analog to the complex numbers? And the answer is yes. And let's see how we can do that. Let's denote by QP bar an algebraic closure of this p-adic field QP. Now, what this means is that any polynomial over, we take any polynomial over QP, so with coefficients in QP, we take all of its zeros and we add all of its roots and we add them to QP. And what we obtain is the field QP bar. So this is a field where every polynomial with coefficients in QP has zeros. And what happens here, which is very different from what happens with R, is that now the degree of this field extension is going to be infinite. So this means that there exist irreducible polynomials over QP of arbitrarily large degree, which is very different from what happens over R, where the largest degree of an irreducible polynomial is equal to 2. For example, x squared plus 1, which gives us the imaginary number I. So this degree 2 extension is the algebraic closure of I and gives us the field of complex numbers C. So here now, this is a degree 2 extension. Now, this is a big difference that will not disappear when constructing the analog, the p-adic analog of the field C. So we can't take QP bar to be directly this analog. Why? Well, because the properties that distinguish the field of complex numbers is that it is at the same time complete with respect to the absolute value, and it is algebraically closed, meaning it's the algebraic closure of the field R. And for now, this new field, this algebraically closed field QP bar, it is not complete with respect to the p-adic norm. So there is a way to uniquely extend the p-adic norm from QP to QP bar, but unfortunately, it does not render the field QP bar complete. So there is something lacking to it. And all we have to do, fortunately, is complete it with respect to this norm. So take the limits of its Cauchy sequences, and we end up by obtaining this new field, which we denote by CP, which is the p-adic analog of C, and which satisfies both of these properties that I mentioned of C. So it is at the same time algebraically closed, and it is complete with respect to the p-adic norm. Now, I'm going to mention now a property which is somewhat at least useful to visualize QP geometrically. So it's more of a topological property, which is that QP is a totally disconnected topological space. Now, what this means is that if you take a subset of QP, a proper subset of QP, which is connected, then it has to be a point. So there's no connected path connecting any two continuous path connecting any 2 points. Basically, all of the points of QP are sort of isolated one from the other. But this is not the only case of a totally disconnected space that we know. We all already know one totally disconnected space. It's the field Q. For instance, if you imagine how it is represented in the line of R, clearly it's represented as a line. You can connect any 2 points with a continuous path. So it's sort of the opposite of a totally disconnected space. And in it, we have the points of Q, which are not connected one with the other. And that's one way that we can also, but larger than Q, that we can imagine QP. So its points are not going to be connected with one another. Now, in the beginning, I mentioned that these fields QP, well, they are very useful for studying arithmetic properties. And in particular, actually, for the study of existence of solutions of polynomial equations. So let's talk a bit about that now, about the solvability of polynomial equations in general. Now, in the 19th century, and this is a major theorem of Ruffini and Abel, which was further developed also by Galois, they showed that a general polynomial equation cannot be solved through what they call radicals. Now, this means that the operations, the usual operations of addition, subtraction, multiplication, and taking roots is not enough. In particular, that this means that we can't really find a general formula that would allow us to have a solution, to find the solutions of the roots of a general polynomial. Now, given this, mathematicians became very interested in either studying whether one could construct additional functions that would allow to, at least in some sort of generality, find a formula for the solutions, for the roots of a polynomial, not necessarily algebraic. We're saying here that in general it's not possible anyway. Or since, well, we're seeing that in general we can't find exactly pinpoint the solutions, but could we at least approximate them? So in particular, a central role was given to the following question. Do solutions of polynomial equations even exist? We're saying that we can't really find them exactly, at least. We want to approximate them, but even to do that, can we, in general, are we able to tell when solutions of polynomial equations exist? Well, for now, we don't know how to do this. It's a very, very difficult question. And in fact, it's a question that on which mathematicians have worked so much that it is at the root of many tremendous developments in mathematics. Many techniques, many useful techniques in mathematics have been developed while studying this sort of question. So I'm going to give an example of this, which I think really illustrates this principle. It's the famous last theorem of Fermat. So around 1637, a French mathematician called Fermat stated the following. He said that the equation x to the power of n plus y to the power of n equals z to the power of n, when n is strictly larger than 2, does not have solutions in z, meaning does not have integer solutions x, y, z, which would satisfy this additional hypothesis. So x, y, z is different from 0. First of all, let me start by commenting on these hypotheses. So we see this condition that n has to be larger than 2. That's because, well, the cases 1 and 2 are already quite well understood. The case n equal 1 is trivial. And the case n equal 2, well, these are the famous Pythagorean triples. We know that in that case, the equation has infinitely many solutions. And that was known for centuries, even before Fermat, before 1637. So the cases of n equal 1 and 2 are well understood, no problem. What about this second hypothesis, x, y, z different from 0? Well, if we were to allow that x, y, z be equal to 0, then we could also trivially even very easily find infinitely many solutions to the equation. It would suffice, for example, to take x equals 0 and y equals z. And then we would have infinitely many solutions. So Fermat, what he says is that, well, apart from these cases that we already know and are somewhat easier, the equation has no other solutions. And this is, when Fermat wrote this statement, he also said something that is quite famous now, that he had a proof, he knew how to prove it, but that the proof was so long that he did not have the space to write it down. And well, it is not known whether Fermat really knew how to prove his last theorem or not, but in any case, it remained open for more than 350 years in spite of many attempts by many mathematicians, many well-established mathematicians, and the proof ended up indeed being very long. It was around, I think Wiles's proof was around 130 pages long, but it also built on all of the mathematics that was constructed before him, that was developed before his time. So it was finally proven in 1994 by a mathematician, by an English mathematician named Andrew Wiles. And when he presented his proof, even right before he presented it, the statement was considered to be so difficult, this statement of Fermat's last theorem, that by many well-established mathematicians at the time, and I'm quoting here, it was considered as impossible to prove. However, though Wiles did manage to prove it, and the utility of his proof is not only in the fact that he finally closed an open question, which remained open for more than 3.5 centuries, but also it was the fact that to prove that what Fermat had stated was true, Wiles developed many techniques in mathematics, which, and I'm quoting here again, are considered as groundbreaking in terms of the consequences they yielded in the development, in the subsequent development of mathematics, particularly in number theory and arithmetic geometry. And a little bit parenthesis here, this is a big proof, one of the strongest examples of the utility of p-adic numbers, the fact that, well, in his proof, Wiles used these new fields, the fields of p-adic numbers, and this non-Archimedean geometry. So let's see another example of how p-adic numbers are useful for these arithmetic questions. So let's take another equation now. Let's take a polynomial, a multivariable polynomial q, which is written like this. So it's a sum of squares times coefficients with rational coefficients. Now this is what we call a quadratic form. So from now on, when I talk about quadratic forms, you can always imagine that it's a polynomial, a multivariable polynomial that looks like this, and with coefficients in some field. So here we're taking it with coefficients in Q. And it's a very natural question. Now that we're interested in solutions to polynomial equations, well, does the polynomial equation induced by this quadratic form have a non-zero solution over the field of rational numbers? Does it have a rational solution? Now, let us remark that it is quite trivial immediately that if we were to take all of the xi equal to 0, then that would be a solution. It's the trivial solution. So what we're asking is, if we remove this obvious solution, this obvious case, does our equation 1 have any other solutions over the field Q? Okay, so over Q itself, directly like this is a pretty difficult question. What happens, for example, if we allow ourselves to look over R? Does this equation Q, when does this equation 1 given by Q have solutions over R? Well, it turns out that thanks to the nice structure, to the rich structure of the field R, then the answer here is quite easy. In fact, our equation has a non-zero solution if and only if at least one of these coefficients is negative and at least one of them is positive. And then we know that there's always a solution, a real solution. But unfortunately, this is not necessarily enough to help give us an answer over Q. So what helped in that direction a lot, to considerably at least simplify the problem, was the following result. It's known as the Hasse-Minkowski theorem, and it was proven about a century ago. So the Hasse-Minkowski theorem says that our equation, so the one induced by this quadratic form, has a solution over Q if and only if it has, well, we're only talking about non-zero solutions. So if and only if it has solutions over every one of the completions of Q. And these are going to be the fields R and the fields QP for all the prime numbers P. Because I did not mention it at the time, but we saw two types of norms on Q, the absolute value and these new p-adic norms. And it turns out that up to certain equivalence relations, these are the only kinds of norms that we can define over Q. So R and QP are all of the possible completions of the field Q. And so the Hasse-Minkowski theorem, it was historically the first result that proved the utility of p-adic numbers. The Hasse-Minkowski theorem, it sort of shifts the problem of the solvability of equation 1 over the field Q to a problem of solvability over the fields R and QP. And this turns out to be very useful because now, just like we saw in the case of R, thanks to the fact that both of these fields, R and QP, for all prime numbers P, have a better structure, a richer structure than that of Q, well then, this is going to be very helpful to give an answer to the question. And this does allow us to sort of arrive to the answer of the original question of whether the equation 1 has solutions, because now there are effective methods, meaning that by a finite number of steps that we need to check, we can determine whether our equation has solutions over these fields R and QP. And in particular, this nowadays can be easily done by a computer. So the problem was solved basically thanks to this principle of looking over the larger and better fields R and QP. And thanks to the utility of this approach, mathematicians started then looking at more generalized and abstract versions of the same sort of principle. So it's what we call today the local global principle. Now we take F to be a field. So in the Hasse-Minkowski theorem, this was just the field Q, but we can take any other field. We can take QP, we can take a larger field, QP parenthesis T, which we'll see what it is soon. And then we can take larger fields Fi, meaning that F is strictly contained in Fi. For example, in the Hasse-Minkowski theorem, these were the fields R and QP. And then we can take V to be a system of polynomial equations with coefficients F. In the Hasse-Minkowski principle, this was our equation 1. And well, here we're studying this object V only in terms of the local global principle. But these sorts of objects are actually the central subject of study of a very vast and very active domain of research in mathematics called algebraic geometry. So if we come back to the local global principle, what it states with this data is that V has a solution in F if and only if it has solutions in all of the larger fields Fi. And this is exactly what happened in the Hase-Minkowski theorem. Now, of course, the idea, just like there, is to choose the larger fields Fi such that, well, they have a better structure, a richer structure, which enables us to study this question on the left by studying the question on the right much more easily. However, though, we already saw an example of a local global principle which was satisfied. It was the Hase-Minkowski theorem, but this is not always the case. One can nowadays construct many examples where the local global principle is not satisfied. So here is one. For instance, you can take the same choice of F and the same choice of the larger fields Fi as in the Hase-Minkowski theorem, and simply take a polynomial equation where now instead of a quadratic form, we are taking something of degree 3. And that is enough for the Hase-Minkowski theorem to no longer be true, so for the local global principle to no longer be satisfied. And since the question of when the local global principle is satisfied and what are the obstructions exactly for it to be verified, have become an active area of research in mathematics for several decades now. So what I do is study this sort of local global principle, but from a geometric point of view. So for instance, if we were to take the smaller field S to be QP parenthesis T, now this field QP parenthesis T, it's simply the field of fractions of polynomials with coefficients in QP. Then if we work over this field, we can use geometric methods to study this principle. Now, why is this true? Why precisely QP parenthesis T? So let me start by telling you that because of these strange, bizarre behaviors that our non-Archimedean geometry satisfies, there are several approaches to studying these objects. In particular, for example, that of the geometry, the approach of Berkovich, of the geometry of Berkovich, which I use in my work. So if we look at one-dimensional objects, so basically curves in this geometry, well, let's start by comparing what happens over R. So for instance, if you take the projective line over R, what you obtain is a circle. This becomes slightly more complicated when you take the Berkovich version of the projective line. What it becomes is this sort of infinitely branched graph. So you have branching everywhere, and since it contracts to a point, it's what we call sometimes an infinitely branched tree. So this may seem a bit surprising that, well, we're going from something so simple to something that seems so complicated, but its intricate structure is the reason that we have more information by working on this curve, on this projective line, which means that when we want to prove a local global principle, well, we have at our disposal more things to use. So what is the relationship of this object with QP parenthesis T? Well, it turns out that we can define certain functions over this curve, we called meromorphic functions, and they form a field which is precisely QP parenthesis T, which means that when we want to study the local global principle over QP parenthesis T, one can directly work over this curve. Basically, then we will have at our disposal at the same time the topological and the analytic structure of this object here, this infinitely branched tree. So let me tell you a bit about the structure of this tree, how we can construct it. Now, for that, I'm going to need the notion of semi-norm. It's slightly less stronger than the notion of norm. So a semi-norm on the ring of polynomials over QP is going to be a function such that, well, the first condition simply means that the function respects the p-adic norm. So the evaluation of any p-adic number is simply going to be its p-adic norm. Then it's also going to be multiplicative. And finally, it's going to satisfy the triangle inequality. And why are these semi-norms important? We will see soon. First of all, let me give you some concrete examples. So if you were to take A to be in QP, a p-adic number, and R a real number, then one way to construct a semi-norm like here would be to simply evaluate any polynomial at the point A, at the p-adic number A, and then take the p-adic norm. Another more general way and very technical is the following. So you can take some positive R and you can take a polynomial, write it around t in the base of t minus a, and then you associate to it this quantity. And this is also going to be a semi-norm. And in particular, one can show that it depends only on the closed disk centered at A and of radius R. And why are these important? Well, because these semi-norms are precisely the points of our infinitely branched tree. So let's take here the element A, the p-adic number A. We can associate to it a line containing all of these points of these semi-norms eta AR for R that varies from 0 to infinity. You can do the same thing for B, except that since I told you in the beginning that every point of a disk is its center, so as soon as B enters a disk centered at A, it's also going to be a center of that disk. So the two lines are eventually going to coincide. And we can do that for all of the points of QP, and we end up obtaining what we just saw, this infinitely branched tree, where the points are precisely these objects that we just defined, which are somewhat less stronger than norms, and we call them semi-norms. So how does this help us obtain a local global principle? Well, let's see. Let's take V to be a system of polynomial equations defined over QP of T. So this is the same notation that we took when I talked about, when I talked about the local global principle. Usually to show local global principles, we need some additional hypotheses, but I won't talk about them here. For example, one can take quadratic forms, just like before, the equations induced by quadratic forms. And then this hypothesis that I'm not talking about comes down to what is written here, that the special orthogonal group acts transitively on this system, the corresponding system determined by Q. So what I do is that I establish a correspondence between, well, the arithmetic language and a geometric language. So I associate to the field QP parenthesis T, which is going to be the field F in the local global principle, the entire Berkovich curve. So this was the infinitely branched tree. And to the larger fields Fi, I associate the points of the curve. And now the local global principle can be translated as follows. So V has a solution over the Berkovich curve, meaning a solution that is a global meromorphic function, because that's how I establish the correspondence, by using meromorphic functions. Now, if and only if this system of polynomial equations has a solution over all the points of this curve, meaning solutions that are local meromorphic functions in the Berkovich curve. How does it work? Well, I'm just going to give you a slight idea. So if we assume that V has local solutions, then it means that for any point, we can construct a neighborhood of it such that inside the neighborhood, V has solutions everywhere. So by using the nice structure of the tree of this curve, and by zooming a bit and refining, one can always assume to be in this setting here, drawn here, so that the neighborhoods where the local solutions exist only intersect at the boundaries, in these, which I drew in blue. And then the nature of V, now this is quite difficult to prove actually, implies that one can suppose that these local solutions, which are simply local meromorphic functions, are compatible in these blue intersections. And since they are simply meromorphic functions which are compatible on the intersections, well, we can glue them together and obtain a solution to V that is a meromorphic function over the entire curve, the entire tree, meaning a solution over QP parenthesis T. And this is how we can use this geometric approach to obtain a local global principle. Now, from this one can show in a certain way more classical versions of the local global principle. For example, one can show that our system of polynomial equations V has a solution in the field QP parenthesis T if and only if it has solutions in certain completions of this field. So this is more classical because in a certain way it resembles to the Hasse-Minkowski principle. There we were working over the field Q, and we had as larger fields the completions of Q. And this is what we have here too. We have completions of the field we are working over, so the field QP parenthesis T. So now this helps us shift the problem of existence of solutions to polynomial equations over these completions. And in concrete terms, if we were to work with quadratic forms, well then one can push things a bit further by studying what happens over these completions and show the following. If P is different from 2, because if P is equal to 2, then quadratic forms may tend to have erratic behavior. Well, if P is different from 2, then the quadratic form given like this with non-zero coefficients over QP parenthesis T has a non-trivial 0 if n is larger or equal to 9. So basically, as soon as our quadratic form is given with more than 9 variables, we immediately know that it has a non-trivial 0. And this is very different with what happens, for example, over R, because then one can construct quadratic forms with arbitrarily large n such that they have no non-trivial zeros over R parenthesis T. So I think that was my last remark. I will stop here. And thank you for your attention.
Thank you, Vlerë. That was a very clear and wonderful presentation.
Thank you very much.
I enjoyed very much, and of course, I think to see this generalization at the end, it's quite interesting. I think for the students out there, it's one of the things to bear in mind is that sometimes you need to enlarge your space in order to have more freedom to add structure so that you can solve a problem. I don't know if anyone has a question, comment to make. If you have any questions or comments, you are welcome to raise your hand. No? If nobody has a question, I have a very general question. So you were talking about these Berkovich curves. What would be a way for you to generalize your problems and your interest? I mean, in terms of algebraic geometry, in terms of dimensions.
Well, I mean, the question immediately poses.
This is very general, of course.
Well, I mean, yeah, but this is over curves. So
exactly.
An immediate question is whether we can do it over higher dimensional space. And I think that is one of the most motivating things that pushed me to work with this geometric approach. So I started, some of my past work, I developed a strategy to work on the higher dimensional case. It turns out that it becomes much more difficult, at least much more technical to deal with. I have partial results. I started by studying fibers of relative curves. And I showed that it can be done around certain fibers. So the next step now is to show that it can be done over certain fibers that, well, I couldn't manage to include, but I think that could be done. And then the next more difficult step would be to see whether one can go from the fibers of a relative curve to the entire relative curve. So that, I think that is a pretty difficult problem. I don't know really how to tackle it yet. But yeah, that would be one possible generalization.
And could I ask one more just general question? What methods do you use? What is do you introduce new methods? Do you use methods of others? What is your approach? How do you tackle this problem?
So it's all hidden here, basically here on this third point, which, like I said, it's not very easy to show. I use this technique called patching. Well, a version that I developed of this technique, because the technique itself has a very long tradition. I mean, it's inspired from techniques in complex analytic geometry. Then we can see other versions of it being applied to study the inverse Galois problem. And then there is an algebraic version to study the local global principle, but which, well, has its limits, because then it's really difficult to imagine going to higher dimensional spaces. So what I do is that I adapt and extend this algebraic patching to these Berkovich spaces, so to these trees, infinitely branched trees. And that, well, works out. It works out quite well, because the patching becomes very, very geometric, like I tried to explain here by hiding many things. But it turns out that in the end, we can interpret it like some sort of gluing of meromorphic functions. So that's the technique I used. And that's, I think, the technique that can be used and can be generalized for the higher dimensional case as well.
All right. So thank you. I think nobody has raised their hand yet. So if that is the case, I want to thank you again, and I will switch to Albanian since
Okay.
Po, më thënë, faleminderit shumë edhe një herë Vlerë, jashtëzakonisht për prezantimin shumë të qartë, të qafshëm edhe interesant, edhe me vlerë. Tash, ky është seminari i parë i një serie që do të vazhdoj. Temat do të jenë të ndryshme, por qëllimi do të jetë gjithmonë që të kemi një folës që marrin prezantime që janë të qafshme për një audiencë të gjerë. Në fillim fare përmenda që është regjistruar seminari, kështu që ndoshta në një moment do ta gjeni veten tuaj në YouTube. Do të shohim. Tash varet edhe prej universitetit tonë. Kështu që në qoftë se nuk ka dikush tjetër, okay. Astrid Sadiku, nuk e di apo e sheh Vlerë Mehmeti?
Paul, is there any symmetry as a consequence of this? What do you mean by symmetry?
Astrid Sadiku, do t'ja jap fjalën. Po tentoj me aktivizu mikrofonin e tij. Në Astrid, nëse keni pyetje lejesht, e aktivizoni mikrofonin edhe flesni. Pyetja, dakord. Pyetja e Astridit është a ka ndonjë simetri? Problemi është që nuk është e qartë për çfarë simetrie bëhet fjalë.
Jo, nuk po e kuptoj. Nëse mundeni me sqaru pak me shkrim, ose nëse jo mundeni të thënë me më shkruaj dhe email, nuk ka problem.
Po, nëse ka mundësi, në fakt, Vlerë, a ju prish punë në qoftë se na dërgoni prezantimin tuaj, slajdet e juaja. Në qoftë se keni mundësi, në qoftë se, kështu që pastaj unë ua përcjelli gjithë këtyre pjesëmarrësve që kanë qenë. Edhe kështu që pastaj ata mund ta vazhdojnë diskutimin me juve.
Sigurisht, mundem me t'i dërgu në email. Okej. Mundem emailin, mundeni me gjetë faqen time në internet, ose mundem me shkruaj këtu.
Po.
Okej.
Shkëlqyeshëm. Bukur, atëherë shpresoj që e kemi filluar një traditë të bukur edhe të dobishme, që po vjen shumë mirë që po shoh shumë fytyra të njohura, dhe do ta vazhdojmë seminarin e radhës në muajin dhjetor, do ta merrni një email për kohën edhe saktë edhe titullin, sapo që përcakton ato plotësisht, dhe një herë e falenderojmë Vlerën, e falenderoj në emër të gjithë juve, në emër të departamentit, në emër të kolegëve, edhe mirupafshim Vlerë dhe mirupafshim të gjithë. Faleminderit.
Faleminderit për ftesën, ishte kënaqësi.
A mund vetëm një falënderim në fund, lutem.
Po profesor, veç unë, profesor Ramadan Diman.
Unë e përcjella këtë prezantim, po edhe më pëlqeu shumë, por edhe prezantimi ishte shembullor, ishte prandaj Vlerës edhe të tjerë ju dëshiroj shumë suksese në të ardhmen.
Faleminderit shumë profesor.
Faleminderit profesor.
Ju faleminderit.
Faleminderit shumë. Nëse nuk ka dikush tjetër, atëherë besoj që është momenti adekuat për me shku në drekë, me mbaru drekën, ose me vazhdu pjesën e dytë të ditës. Faleminderit, mirupafshim gjithë të mirë.
Mirupafshim.
Mirupafshim.
Mirupafshim, faleminderit Vlerë.